Welcome back to our digital electronics series. In today's episode, we're exploring two essential components that bridge the digital and analog worlds: analog to digital converters, ADCs, and digital to analog converters, DACs. These devices play a crucial role in modern electronics, allowing digital systems to interact with real-world analog signals. Let's dive into how ADCs and DACs work, their different types, and where they are used. Let's start with analog to digital converters, or ADCs. An ADC converts a continuous analog signal, like sound or temperature, into a digital signal that a computer or digital device can process. This conversion is crucial because digital systems, like microcontrollers or computers, operate using binary data, zeros and ones. The process involves sampling the analog signal at specific intervals and then quantizing each sample to a digital value. The accuracy of this conversion depends on two main factors: the sampling rate and the resolution of the ADC. There are several types of ADCs, each suited for different applications. The most common types are successive approximation, flash, and sigma-delta ADC. Successive approximation ADC are widely used in microcontrollers. These ADCs provide a good balance between speed and accuracy by approximating the input signal step by step. Flash ADC are the fastest type, ideal for high-speed applications like video processing, but it comes with higher power consumption and cost. Sigma-delta ADC are popular in audio applications. These ADCs offer high resolution and excellent noise performance, perfect for converting analog signals in music and voice. On the other side, we have digital to analog converters, or DACs. A DAC performs the opposite function of an ADC. It converts digital data back into an analog signal. This is essential for devices that need to output analog signals, such as audio amplifiers, TVs, and motor controllers. The DAC reads digital data and generates a corresponding voltage or current to create a continuous analog signal. The fidelity of this analog signal is influenced by the resolution and the speed of the DAC. Similar to ADCs, there are various types of DACs. Our two-ladder DAC type uses a simple resistor network to convert digital codes into an analog signal. It's commonly used in audio equipment due to its simplicity and good performance. Weighted resistor DAC is an older design that uses resistors weighted according to their binary position. It's less common now but still found in some low-cost applications. Delta Sigma DAC are widely used in high-fidelity audio applications. These DACs provide excellent noise shaping and are ideal for high-resolution audio playback. ADCs and DACs are everywhere in modern electronics. For example, ADCs are used in digital oscilloscopes to convert analog signals for analysis, in digital cameras to convert light into digital images, and in sensor systems to digitize temperature, pressure, or humidity data. DACs, on the other hand, are critical in any application where digital information needs to be output as an analog signal. This includes digital audio players, signal generators, and in various control systems like those used in industrial automation. And that's an overview of ADCs and DACs, the essential components that connect the digital and analog worlds. From capturing real-world signals to driving displays and actuators, these converters play a vital role in our digital lives. Thanks for tuning in. If you enjoyed this video, make sure to like, share, and subscribe for more deep dives into digital electronics. See you next time.